Today we have second day session of 2 day science webinar. Hello, hello, hello. Hello, hello. Mic checking. Hello, hello, hello. Is it audible? ವೆಬಿನಾರ್ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ ಅಂತ ಹೇಳಿ ಆದ್ರೆ ಎರಡನ್ನೂ ಸರಿ ಹೇಳಿ ಪ್ಲೀಸ್. Hello, hello. Welcome to the 2 days international webinar, and the session will going to start within 40 minutes. Is it audible? Sir, what about it?
ಹಲೋ ಸರ್.
ಬಂತು ನೋಡ್ರಿ ಸರ್, ಬಂತು ನೋಡ್ರಿ.
ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಸರ್. ಸರ್ ಸ್ಕ್ರೀನ್ ಸ್ವಲ್ಪ ನೋಡಿ ಸರ್, ತಮ್ಗೆ ಹೆಂಗ್ ಬೇಕು?
ಏನಂದ್ರಿ ಸ್ಕ್ರೀನ್ ರೀ?
ಸರ್
ಶೇರ್ ಮಾಡ್ರಿ.
ಅಲ್ಲ, ಫೇಸ್ ತಮ್ದು ಅಪ್ ಟು ಇದಕ್ಕೆ ಐತೆ ಸರ್, ಏನಂತಾರ ಮುಖದವರೆಗೂ ಅಂದ್ರೆ ಕೆಳಗಡೆ ಕಂಪ್ಲೀಟ್ ಫೇಸ್ ಕವರ್ ಆಗ್ತಾ ಇಲ್ಲ ಸರ್.
ಹೌದಾ? ಈಗ ಸಾಕಾಗಿ ಕರೆಕ್ಟ್ ಇಲ್ರಿ ಸರ್ ಈಗ?
ರೈಟ್ ಸರ್, ರೈಟ್. ಇವಾಗ ಓಕೆ.
ಈಗ ಓಕೆ ಅಲ್ರಿ?
ರೈಟ್ ಸರ್, ನೋ ಪ್ರಾಬ್ಲಮ್. ಇವಾಗ
ಓಕೆ ಸರ್.
ಸೌಂಡ್ ಸರ್ ನಂದು ಕ್ಲಿಯರ್ ಐತ್ರಿ, ತಮ್ಗೆ ಕ್ಲಿಯರ್ ಆಡಿಬಲ್ ಐತಲ್ ಸರ್ ಸೌಂಡ್?
ಹೌದು ಸರ್, ಹೌದು ಸರ್, ಕ್ಲಿಯರ್ ಇದೆ ಸರ್ ನನಗೆ. ನನ್ನ ವಾಯ್ಸ್
ತಮ್ದು ಇದೆ, ತಮ್ದು ಐತಿ ಸರ್. ಆಡಿಯೋ ವಿಸಿಬಲ್ ಐತ್ರಿ. ಇದು ಆಡಿಯೋ ಕ್ಲಿಯರ್ ಐತಿ, ವಿಡಿಯೋನು ಕ್ಲಿಯರ್ ಐತಿ, ಸಮಸ್ಯೆ ಇಲ್ಲ.
ಫೈನ್ ಸರ್, ಫೈನ್.
ಇಟ್ ವಿಲ್ ಸ್ಟಾರ್ಟ್ ಇನ್ 4 minutes ಸರ್.
ಓಕೆ ಸರ್, ನೋ ಪ್ರಾಬ್ಲಮ್. ನಾನು 4 minutes ಆದ್ಮೇಲೆ ಶೇರ್ ಮಾಡ್ಲಂದ್ರಲ್ಲ?
ಸರ್, ನಾನು ತಾವು ಸ್ಕ್ರೀನ್ ಆಗಿ ಇರ್ತೀರಿ. ಇದು ನಾನು ವೆಲ್ಕಮ್ ಮಾಡ್ತೀನಿ ಫಾರ್ಮಾಲಿಟಿ ವೆಲ್ಕಮ್ ಆದ್ಮೇಲೆ
ಒಂದ್ಸರ್ತಿ ಶೇರ್ ಮಾಡ್ತೀನಿ ತಡ್ರಿ ಸರ್. ನಾವು ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್. ಓಕೆ ಸರ್, ಒಂದೇ ನಿಮಿಷ.
ಸರ್.
ಸರ್ ಈಗ ಕಾಣಿಸಿದ್ರೆ
ಬರ್ತದೆ ಸರ್. ಇಸ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಅಂತ ಬಂತು, ಇನ್ನು ಸ್ಕ್ರೀನ್ ಬಂದಿಲ್ಲ ಸರ್.
ಹೌದ್ರಾ?
ಸರ್.
ಒಂದೇ ನಿಮಿಷ ಸರ್. ನೋಡ್ರಿ ಸರ್ ಈಗ.
ಸರ್, ಇನ್ನು ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಇಲ್ಲ ಸರ್. ಇನ್ನು ಇದು ಗೂಗಲ್ ಮೀಟಿಂಗ್ ಇದೆ ಸರ್, ಯೂಟ್ಯೂಬ್ ಬರ್ತೈತೆ ನೋಡಿ ಸರ್.
ಇಲ್ಲಿ ನನಗೆ ಸ್ಕ್ರೀನ್ ಶೇರಿಂಗ್ ಅಂತ ತೋರಿಸುತ್ರಿ ಸರ್.
ಸ್ಕ್ರೀನ್ ಶೇರಿಂಗ್ ಅಂತ ತೋರ್ಸಾಕೈತೆ ಸರ್.
ಅಂದ್ರೆ ಮೀಟ್ ಗೂಗಲ್ ಇಸ್ ಶೇರಿಂಗ್ ಯುವರ್ ಸ್ಕ್ರೀನ್ ಅಂತ ಬರ್ತದೆ ಸರ್. meet.google.com is sharing your screen.
ಇಲ್ಲ ಸರ್, ತಮ್ದು ಬರೀ ಫೇಸ್ ಅಷ್ಟೇ ಐತ್ರಿ, ಸ್ಕ್ರೀನ್ ಬರ್ತಾ ಇಲ್ಲ ಸರ್. ಪ್ರೆಸೆಂಟೇಷನ್ ಬರ್ತಾ ಇಲ್ರಿ.
ಓಕೆ ಸರ್, ಇನ್ನೊಂದ್ಸರ್ತಿ ತಡ್ರಿ. ಹಂಗಿದ್ರ ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಕೊಟ್ಟೆ.
ಸರ್,
ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಕೊಟ್ಟೆ. ಪ್ರೆಸೆಂಟ್ ನಾವು your entire screen.
ಎಸ್ ಸರ್. ಈಗ ಅದು ಪ್ರೆಸೆಂಟೇಷನ್ ಓಪನ್ ಮಾಡಿ ಸರ್. ಪ್ರೆಸೆಂಟೇಷನ್ ಈಗ ಬರ್ಬೇಕು ಸರ್.
ಬಂತು ನೋಡ್ರಿ ಸರ್. ಬಂದ್ರಿ ಈಗ?
ಇಲ್ಲ ಸರ್, ಇನ್ನೂ ಬರ್ತಾ ಇಲ್ಲ, ಬರೀ ತಮ್ಮ ಫೇಸ್ ಬರತೈತೆ ಸರ್.
ಹೌದ್ರಾ? ಒಂದೇ ನಿಮಿಷ ಸರ್. ಓಕೆ, ಇಲ್ಲಿಂದ ಹೋಗ್ತೇನೆ ನೋಡ್ರಿ. ಸ್ಟಾಪ್ ಪ್ರೆಸೆಂಟಿಂಗ್. ಓಕೆ, ಸ್ಟಾಪ್ ಪ್ರೆಸೆಂಟಿಂಗ್. ಪ್ರೆಸೆಂಟ್ ನಾವು ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್. ಶೇರ್. ಓಕೆ, ಈಗ ನೋಡ್ರಿ ಸರ್ ಏನಾದ್ರು?
ಇಲ್ಲ ಸರ್, ಸ್ಕ್ರೀನ್ ಮೇಲೆ ಬರೀ ತಮ್ದ ಬರತೈತೆ ಸರ್. ಇಲ್ಲಾಂದ್ರೆ ಒಂದು ಕೆಲಸ ಮಾಡ್ಬೋದು ಸರ್, ತಾವು ಅದನ್ನ ಕಳಿಸಿದ್ರೆ ನಾನು ಡೌನ್ಲೋಡ್ ಮಾಡಿ ನಾನು ಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೀನಿ ಸರ್.
ಸರ್, ಅದು 26 MB ಅದ ರೀ. ಈಗ ನೋಡ್ರಿ ಸರ್. ಈಗ ಆಯ್ತ್ರಿ?
ಇಲ್ಲ ಸರ್, ಇನ್ನು ತಮ್ಮ ಫೇಸ ಬರತೈತ್ರಿ.
ಶೇರಿಂಗ್ ಕೊಟ್ಟೆ ನಾನು. ನಿನ್ನೆ ಮಾಡಿದ್ವಲ್ರಿ ಸರ್, ಅದಕ್ಕೋಸ್ಕರ ನಾನು ಒಂದ್ಸರ್ತಿ ರಿಹರ್ಸಲ್ ನೋಡ್ಕೊಂಡು ಬಿಟ್ಟೆ.
ಸರ್.
ರೂಮ್ ಟ್ಯಾಬ್
ಸ್ಕ್ರೀನ್ ಬರುತ್ತಲ್ಲ.
ಪಿಪಿಟಿ ಏನಾದ್ರೂ ಇದನ್ನ ಮಾಡಿದೆ ಅಂದ್ರೆ ಶೇರ್
ಮಾಡ್ಬೋದು. ಇಲ್ಲ, ನಮಗ್ ಮಾಡಿಲ್ಲ, ಅವ್ರು ಮಾಡಕತ್ತಾರ ಪ್ರೆಸೆಂಟಿಂಗ್. ಬಟ್ ಇಲ್ಲಿ ಸ್ಕ್ರೀನ್ ನಾಗ ಬರ್ತಾ ಇಲ್ಲ ಅದು.
ಇಲ್ಲ, ನಮ್ಗೆ ಕಳ್ಸಿದ್ನಂದ್ರೆ ನಾವಿಲ್ಲ ಅಟ್ಯಾಚ್ ಮಾಡಿದ್ಮಲ್ಲ. ಮೊನ್ನೆ ಏನ್ ಮಾಡಿದ್ರು?
ಇಲ್ಲ, ಅವರು 25 MB ಐತೆ ಅಂತಾರೆ ಸರ್. ಸ್ವಲ್ಪ ಸೈಜ್ ಜಾಸ್ತಿ ಇರ್ಬೋದು.
ಸರ್, ಈಗ ಬರ್ತಾ ಇಲ್ಲ ಅಂದ್ರೆ
ಪ್ರೆಸೆಂಟೇಷನ್?
ಇಲ್ಲ ಸರ್, ಫೇಸ್ ಅಷ್ಟೇ ಬರತೈತೆ, ಸ್ವಲ್ಪ ಇದು ಬರ್ತಾ ಇಲ್ಲ.
ಓಕೆ, ಈಗ ನನ್ಗೆ ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಅಂತ ಅದ ರೀ. ನನಗೆ ಆಪ್ಷನ್ ಹೈಡ್ ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಅಂತ ಅದ ನೋಡ್ರಿ
ಸರ್. ಈಗ ತಾವು ಪ್ರೆಸೆಂಟ್ ನಾವು ಅಂತ ಅಂತಿರಲ್ಲ ಸರ್, ಪ್ರೆಸೆಂಟ್ ನಾವು ಆದ್ಮೇಲೆ.
ಸರ್, ಪ್ರೆಸೆಂಟ್ ನಾವು ಅಂದರೆ
ಕ್ಯಾಮ್ರಾ ಆನ್ ಮಾಡ್ಕೊಳ್ರಿ.
ಕ್ಯಾಮ್ರಾ.
ಸರ್, ಪ್ರೆಸೆಂಟ್ ನಾವು ಅಂತೀನ್ರ, ಅಲ್ಲಿ ಯುವರ್ ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್ ಅಂತ ಬರ್ತದ್ರಿ. ಅದು
ನೋಡ್ರಿ, ಅವ್ರು ತೆಗೆದ್ಬಿಟ್ರಿ ನೀವು. ಇವಾಗ ನಾವು ಕಾಣ್ತಾ ಇದೀವಿ
ಸರ್. ನಾವು ಕಾಣ್ತಾ ಇದೀವಿ ಸರ್.
ಹೌದು, ನೀವು ಕಾಣ್ತಾ ಇದ್ದೀರಿ ಸರ್. ಕಾಣ್ತಾ ಇದ್ದೀರಿ.
ಹೌದು, ಪ್ರೆಸೆಂಟ್
ಸರ್, ತಾವು ಕಾಣ್ತಾ ಇದೀರಿ. ಈಗ ಪಿನ್ ಮಾಡಿ ತಮ್ಗೆ ಪಿನ್ ಮಾಡಿದ್ ಸರ್. ಇಲ್ಲಿ ತಮ್ದು ಸ್ಕ್ರೀನ್ ಈಗ ಶೇರ್ ಆಗ್ಬೇಕು ಸರ್. ನೋಡ್ರಿ, ಟ್ರೈ ಮಾಡ್ತೀರಿ ಇನ್ನೊಂದ್ಸಲ. ಅಷ್ಟು ಹಂಗೆ ಬ್ಲಿಂಕ್ ಆಗಿತ್ತು, ಬಟ್ ಬರ್ತಾ ಇಲ್ಲ.
ಏನೋ ಒಂದು ಆಪ್ಷನ್ ಬಂದೋಯ್ತು ನೋಡ್ರಿ.
ಸರ್, ಈಗ ನನಗೆ ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಅಂತ ಬರ್ತಾ ಇದೆ.
ಟಚ್ ಮಾಡಿ ಯುವರ್ ಎಂಟೈರ್ ಈ ವಿಂಡೋ ಅಂತ ಪ್ರೆಸ್ ಮಾಡಿ ನೋಡ್ರಿ. ಏನ ಶೇರ್ now
let you take over but compare the bench project share now.
ಬಂದ್ರೆ
ಸರ್.
ಅದು ಅವ್ರ ಶೇರ್ ಅಂತ ಆಗ್ಬೇಕಿತ್ತು, ನಮ್ಮ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಯ್ತು. ಅದೇ ತರ ಅವ್ರದ್ದು ಏನಾದ್ರು ಸ್ಕ್ರೀನ್ ಶೇರ್
ಸರ್ ನನಗಿಲ್ಲಿ ಬರ್ತದ್ರಿ, ಯು ಆರ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಟು ಎವ್ರಿ ಒನ್ ಅಂತ ಬರ್ತಾ ಇದೆ ಸರ್ ಈಗ.
ಹಾ ಸರ್, ನಾವಿಲ್ಲಿ ಶೇರ್ ಅಂತ ಇದು ಮಾಡ್ತೀವಿ ಸರ್, ಆಪ್ಷನ್ ಐತಿ ನೋಡೋಣ ಸರ್.
ಹಾ, ಯು ಆರ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಟು ಎವ್ರಿ ಒನ್ ಅಂತ ಬರ್ತಾ ಇದೆ ಸರ್ ನನಗೀಗ.
ಹಾ ಸರ್, ಯು ಆರ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಆನ್ ದ ಸ್ಕ್ರೀನ್.
ಬಂದ್ರಿ ಸರ್?
ಇಲ್ಲ ಸರ್, ಇಲ್ಲ.
ನಮ್ದು ಶೇರ್ ಆಯ್ತು.
ಹಾ ಸರ್, ಕೇಳ್ರಿ.
ಬರ್ಲಿಲ್ರಿ?
ಇಲ್ಲ ಸರ್, ಬರ್ತಾ ಇಲ್ರಿ. ಅದ್ ನೋಡ್ರಿ ಏನ್ ಬರತೈತೆ ನೋಡಿದ್ರಾಗ.
ಸರ್ ನನಗೆ ಕ್ಲಿಯರ್ ಅದ ರೀ, ರೆಸ್ಯೂಮ್ ಯುವರ್ ಪ್ರೆಸೆಂಟೇಷನ್. ಓಕೆ,
ಹಾ ಸರ್.
ಈಗ ನೋಡ್ರಿ ಸರ್. ಬರ್ತಾ ಇಲ್ರಿ?
ಇಲ್ಲ ಸರ್, ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಾ ಇಲ್ಲ.
ಒಂದೇ ನಿಮಿಷ ತಡೀರಿ, ಇನ್ನೊಂದ್ಸರ್ತಿ ನಾನು ಎಲ್ಲದನ್ನು ಸ್ಟಾಪ್ ಪ್ರೆಸೆಂಟಿಂಗ್ ಅಂತದೆ ಸರ್ ನನಗೆ.
ಸರ್ ಸ್ವಲ್ಪ ಟೆಕ್ನಿಕಲ್ ಪ್ರಾಬ್ಲಮ್ ಆಗಿತ್ತು, ಒಂದು ಇನ್ಫಾರ್ಮೇಶನ್ ಬೇಕಾಗಿತ್ತು. ತಾವು ಬಂದ್ರೆ ಒಳ್ಳೇದಿತ್ತು. ಏನಂದ್ರೆ ಅದು ಸ್ಲೈಡ್ ಶೇರ್ ಆಗ್ತಾ ಇಲ್ಲ ಅವ್ರದ್ದು. ಹಾ ಸರ್, ಆಪೋಸಿಟ್. ಹಾ ಅಲ್ಲ, ಅವ್ರ ಕಡೆಯಿಂದನೂ ಶೇರ್ ಮಾಡ್ಬೋದಾ? ಎಲ್ಲಿ ಪ್ರೆಸೆಂಟ್ ಅಂದ್ರೆ? ಹಾ 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 ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್. ಹಾ, ಯುವರ್ ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್
ನಮ್ದೈತೆ ಅದು.
ನಾನು ಅದನ್ನೇ ಮಾಡೀನಿ ಸರ್, ನಾನು ಅದನ್ನೇ ಮಾಡೀನಿ. ನಾನು ಎಂಟೈರ್
ಹಾ
ಸ್ಕ್ರೀನ್
ಸರ್, ಪ್ರೆಸೆಂಟ್ ನಾವು ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್ ಪ್ರೆಸೆಂಟೇಷನ್ ಲೋಡ್ ಆದ್ರೆ,
ಬಟ್ ಅವ್ರದ್ದು ನಮ್ಮ ಸ್ಕ್ರೀನ್ ಕಾಣ್ತಾ ಇಲ್ಲ.
ಸರ್ ನನಗೆ ಕ್ಲಿಯರ್ ಆಗಿ ತೋರಿಸ್ತಾ ಇದ್ದಾರೆ, ಇಲ್ಲಿ ಸ್ಟಾಪ್ ಶೇರಿಂಗ್ ಅಂತ ಅದಾರೆ. ಹಲೋ, ನೀವು ಮ್ಯೂಟ್ ಇದ್ರಿ ಸರ್. ಹಲೋ,
ಏನ್ ಮಿಸ್ ಆಗಿತ್ತು
ಸರ್?
ಹೇಳ್ರಿ ಸರ್.
ಸರ್ ನಿಮ್ದು ಸ್ಕ್ರೀನ್ ಬರ್ತಾ ಇದೆಯಾ ಸರ್ ಇವಾಗ?
ನನಗೆ ನೀವು ಕಾಣಿಸ್ತಾ ಇದ್ದಾರೆ ಸರ್, ನನಗೆ ತೋರಿಸ್ತಾ ಇದೆ ಅದು ಯುವರ್ ಸ್ಕ್ರೀನ್ ಇಸ್ ಬಿಂಗ್ ಶೇರ್ಡ್ ಅಂತಾನು ತೋರಿಸ್ತಾ ಇದೆ ಸರ್. ಶೇರಿಂಗ್ ಯುವರ್ ಸ್ಕ್ರೀನ್ ಅಂತಾನೆ ಇದೆ.
ಹಾ ಸರ್, ರೈಟ್ ಸರ್.
ಕಾಣಿಸ್ತಾ ಇದೆ ಸರ್ ಈಗ?
ಹಾ ಸರ್. ಶಾಣಪ್ ಸರ್, ಶಾಣಪ್ ಸರ್,
ಸ್ಕ್ರೀನ್ ಕಾಣಿಸುತ್ತೆ ಸರ್ ಈಗ ನಂದು ಶೇರ್ಡ್ ಸ್ಕ್ರೀನ್?
ಅವ್ರದ್ದು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ಬೇಕಲ್ಲ ಬರ್ರಿ. ಈಗ ಅವ್ರದ್ದು ಹೊಸದು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಾ ಇಲ್ಲ.
ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಿಲ್ಲ. ವಿಡಿಯೋ ಇದು ಅವ್ರಲ್ಲ ಸರ್, ಫೋನ್ ಹಚ್ಚಿ ಮಾತಾಡೋಣ ಅಂತ ಇದು ಮಾಡ್ರಿ.
ಇದು ಅವ್ರದ್ದು. ಈಗ
ಅವ್ರ ವಿಂಡೋಗೆ ಹೋಗಂತ ಹೇಳ್ರಿ. ವಿಂಡೋಗೆ ಹೋಗಂತ ಹಚ್ಚಿ ಹೇಳ್ಬಿಡ್ರಿ ಸರ್. ಮಾತಾಡ್ರಿ, ನೀವು ಮಾತಾಡ್ರಿ
ಸರ್. ಹೊರಟಿ ಸರ್. ಸರ್ ಏನಿಲ್ಲ, ಅವ್ರದ್ದು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಿರ್ಲಿಲ್ಲ ಸರ್ದು, ಅದಕ್ಕೆ ಅವ್ರದ್ರಿ ಇವ್ರದ್ದು ಎಕ್ಸ್ಪರ್ಟ್ ಅದಾರಲ್ಲ ಆ ಕಡೆಯಿಂದ ಸಬ್ಜೆಕ್ಟ್ ಎಕ್ಸ್ಪರ್ಟ್.
ಸರ್ ನಾನು ಇನ್ನೊಂದ್ಸರ್ತಿ ಲಾಗಿನ್ ಆಗ್ಲಿರ ಬೇಕಿದ್ರೆ. ದೀಪಾ ನನ್ನ ಮೊಬೈಲ್ ಬಂತಾ ಇಲ್ಲಿ? ಹಲೋ ಸರ್, ಹೇಳ್ರಿ. ಓಕೆ, ನನ್ನ ಸ್ಕ್ರೀನ್ ಆಗಿದೆ ಅಲ್ಲ ಸರ್, ಈಗ ಶೇರ್ ಆಗಿದೆ ಅಲ್ರ? ಓಕೆ ಸರ್, ಓಕೆ ಡನ್. ನಾನು ಇಮೇಲ್ ಕಳಿಸ್ಲಿಲ್ಲ ಸರ್ ನಿಮಗೇನಾದ್ರೆ. ಇಮೇಲ್ ನಾನು ನಿಮ್ಗೆ ಅಟ್ಯಾಚ್ ಆಗ್ತಾ ಇಲ್ರಿ ಸರ್, ಅದು ನಾನು ರೆಡ್ಯೂಸ್ ಮಾಡಿ ಕಳಿಸಿದ್ದೆ ಅದನ್ನ. ಈಗ PPT ಆನ್ ಆಗಿದೆ ನೋಡ್ರಿ ಸರ್. ಈಗ ಸರ್ ಕಾಣಿಸ್ತಾ ಇದೆಲ್ರ? F5. ಸ್ಕ್ರೀನ್ ಏನಿದೆ ನೋಡ್ರಿ ಸರ್ ಈಗ. ಓಕೆ ಇದು ಇವಾಗ ಬಂತಲ್ರಿ ಸರ್? ಓಕೆ ಸರ್, ಓಕೆ ಡನ್. ಥ್ಯಾಂಕ್ ಯು. ದುಷು ತಗೊಂಡೋಗಮ್ಮ.
ಸ್ಟಾರ್ಟ್ ಮಾಡ್ರಿ.
ಎಲ್ಲ ಐತೆ, ನಮ್ದು ಬರ್ತಾ ಇಲ್ಲಲ್ಲ ಸರ್. ಶರಣಪ್ಪ ಸರ್, ನಮ್ದು ಬರ್ತಾ ಇಲ್ಲಲ್ಲ ಸ್ಕ್ರೀನಿಗೆ, ನಮ್ದು ಬರ್ತಾ ಇಲ್ಲ ಸರ್.
ಅವ್ರ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡಿರಲ್ಲ ಸರ್,
ಅವ್ರು ಮಾಡಿ
ಫೋಟೋ ಕಾಣಲ್ಲ. ಒಂದ್ 2 ನಿಮಿಷ.
ಮೇಲೆ ಇದು ಅದಲ್ಲ ಫಸ್ಟ್ ಫ್ರಂಟ್
ಅಲ್ಲ ಡೀಟೇಲ್ ಆಗಿ
ಆಮೇಲೆ ಅವ್ರು ಸೆಂಡ್ ಮಾಡ್ಕೊಡಿ. ಸ್ಟಾರ್ಟ್.
Good morning to all the participants. So this is the second day of the international webinar on recent trends in microbes and chemical sciences. Yesterday, Dr. Mantesh B. Patil and Dr. Syed G. Dastigir has given their lectures, and today Dr. Srinivas Budgumpi and Dr. Rohit Chikreddy will be giving their presentation. Firstly, I welcome Dr. Srinivas Budgumpi to give his lecture. As a formality, I will give the brief introduction about the Dr. Srinivas Budgumpi. Sir, it is my great privilege to give a small introduction of you. Dr. Srinivas Budgumpi is presently working as a associate professor and group leader in Center for Nano and Material Sciences, Jain University, Jain Global Campus, Bangalore. His professional experience is from in April 2010 to 2011, he has worked as the postdoctoral researcher in Busan National University, Republic of Korea. In the year 2011-12, he worked as a postdoctoral fellow, University Science Malaysia, and in September 2012 to 2013, he worked as postdoctoral fellow, University Technology Malaysia, and in 2013-14, he worked as a 2014 to 18, he worked as an assistant professor, CNMS, Jain University, Bangalore, and from 2018 till date, he is working as an associate professor in Jain University, Bangalore. His visiting positions are: he was a visiting scientist in the Dipartimento di Scienze Chimiche, University di Padova, Italy. And regarding his education, he has completed his BSc in chemistry from Vijayanagar College, Hospet, India. He has completed his MSc in chemistry from Gulbarga University, Gulbarga in 2005, and he got his PhD from Karnataka University, Dharwad in 2010. His achievement and awards. In 2014, he is the recipient of Y.S. Agsimuddin Felicitation Committee Fund Fellowship for securing highest marks in the MSc first and second semester. In year 2005, he has received a special gold medal from Vasavi Union Charitable Trust, Bangalore, for securing first rank in MSc Chemistry among successful candidates. In 2005 only, he received Miss Mohana Memorial Gold Medal for securing highest marks in analytical, inorganic, and biochemistry branches. He has taken many more branches, many more awards. In the 2011, he has awarded the postdoctoral research fellowship from Pusa National University. In 11-12, he got postdoctoral fellowship from University of Science Malaysia. In 12-13, he got postdoctoral fellowship from Malaysia University. In 13-14, he got postdoctoral fellowship from University of Science. And in 2016, he was a visiting scientist position from Padova, Italy. And regarding his research interests are N-heterocyclic carbon complexes as homogeneous catalyst, NHC complexes as heterogeneous catalyst, biologically relevant NHC complexes, and NHC complexes as fluorescent and luminescent materials. A brief summary of his research supervision. Under his guidance, one postdoctoral fellow has worked. PhDs awarded are 2, and 5 students are working for their PhD with his guidance. And 13 MSc students have done research for their MSc work, and totally he has 74 publications to his credit. So this is the brief summary of the achievements of Dr. Srinivas Budgumpi, Associate Professor and Group Leader, Jain University, Bangalore. Sir, now I welcome you personally from Shri Gavisiddeshwara Arts, Science and Commerce College, Koppal, to present your topic.
Okay, thank you so much. Am I audible?
Yes, sir, audible, sir.
Thank you so much, Dr. Shashikanth, for your kind words. Yes, so I welcome all the participants to this international webinar. Thanks, Professor Dadmi, sir, for inviting me to give a lecture in this particular webinar. And my bonding with SG College has been over a little over 2 decades, ever since I joined for PU classes back in 1998. So Professor Dadmi sir is my first college chemistry guru, in fact, and I thank you, Professor Dadmi sir, for this opportunity. Well, so let us start the seminar. Let us start this talk. The title of my presentation today is Organometallics and Catalysis. Myself, Dr. Srinivas Budgumpi, Associate Professor with Center for Nano and Material Sciences, Jain University, Bangalore. So let us see the contents of my presentation. Just a background of what the topic is covered on, that is organometallics and catalysis. Introduction to what exactly my research work is focused on. In that, the Palladium NHC complexes, synthesis and SEC coupling catalysis. Palladium NHCs for the CH activation catalysis. Nickel NHCs for electrocatalytic glucose detection. Silver, gold, and nickel NHC complexes for electrocatalytic hydrogen evolution reactions. Last 2 bits are the unique ones here. We are the first people to work on glucose sensing application using the NHC complexes and HER, means hydrogen evolution reactions from metal NHC complexes, followed by the conclusions and remarks. Well, so let us understand the background of organometallic compounds initially. Then we will see what exactly I am going to talk about. Right. So organometallic compounds, as name itself indicates, they must be having at least one metal to carbon bonding, These covers variety of compounds starting from metal carbonyl, cyclometylated derivatives, half sandwich metal derivatives, sandwich metal compounds, and the best example for sandwich metal compounds is ferrocene. Half sandwich metal compounds are the CpMn complexes with tricarbonyl compounds. So these are what the organometallic compounds are, while carbenes are also considered as organometallic compounds, but less focus is given on these things because of their highly reactive nature at room temperature, and these carbenes are stable only at lesser temperatures. So suppose liquid nitrogen temperature, that is at minus cryo temperatures, minus 78 degrees Celsius. Hence, it is difficult to deal with these carbenes. That could be the reason behind why people have not worked much on this chemistry. So for carbenes, as name itself indicates, reaction intermediates, organic molecules that are composed of a neutral divalent carbon atom, so which is having 2 non-bonding electrons, as you can see on the screen. So this particular carbon is considered as the carbene carbon because this is divalent. Usually in organic molecules, carbon is tetravalent, Whereas in this particular case, it's divalent carbon atom with the 2 non-bonding electrons. So depending on the position of these non-bonding electrons, these carbenes are classified. These carbenes are classified. So for example, if both the unpaired electrons are present in one orbital, one of the p orbitals, leaving other p orbital empty, we call it a singlet carbene, while these 2 non-bonding electrons reside in one of these last 2 p orbitals, namely 2py and 2pz, we call them as triplet carbenes. Both the types of carbenes are highly reactive, right? Initial work on these carbenes was carried out by Fischer, right? Ernst Otto Fischer, who was a German scientist, got Nobel Prize in 1973 for his discovery of these Fischer carbenes. So Fischer carbenes are having an electron donor substituent, and these are highly nucleophilic in nature. The way how it's given here, right in the first figure, right hand side. So which is a tungsten complex. Dr. Shashikant, am I audible? Hello, Dr. Shashikant, am I audible?
Hello, sir.
Am I audible, Dr. Shashikant? Can I continue?
Because yes, sir. It is everything is okay, sir.
Because I cannot get response from other side, right? I feel that I may not be reachable to everyone. Okay, shall I continue?
Sir. Everyone is muted, sir. That's why.
Okay, sir. Thank you so much. Fine.
Okay,
so
sir.
Fischer carbene. Yes,
you can proceed, sir. You can proceed.
Thank you so much, sir. Fischer carbene is a German scientist who got Nobel Prize for his great discovery of these carbenes in 1973. In 1973, and these carbenes are highly nucleophilic in nature. So please unmute. So please unmute. Please mute. Okay, these Fischer carbenes are having electron donor substituent attached to the carbene-carbon. I would say this is the carbene-carbon here, and the electron donor substituents are attached next to the carbene-carbon, which makes carbene-carbon more nucleophilic. Whereas in the case of Schrock carbenes, another great scientist, Richard Schrock, is an American scientist, is an American chemist who got Nobel Prize again in 2005. So these carbenes are simplest ones but highly reactive. Difference between Fischer and Schrock carbenes are singlet and triplet states. While both the types of carbenes, both Fischer and Schrock carbenes, are highly reactive, therefore their reactivity or isolation of these carbenes seems very difficult, extremely difficult. While in 1991, Dingo et al., again an US research group, they have discovered the persistent carbenes in which these persistent carbenes are having an N-heterocyclic system in them. Means a N-heterocyclic system is having carbene-carbon as part of the heterocyclic system. So which are usually derived from azolium salts, quaternary imidazolium salts. Imidazolium salts are trizolium salts. For example, an azolium salt is given here. An azolium salt is given here means 1,3-dimethylimidazolium chloride, which upon reaction with the base, the C2 proton is deprotonated, and hence a carbene is formed here. Of course, these carbenes are reactive, of course, but not to the extent of Fischer and Schrock carbenes. My research area is focused in the reactivity and applications of these carbene complexes. We are making use of these carbene complexes as the donor ligands, and these carbenes are highly strong sigma donors. So I will see the introduction to these NHCs. It means N-heterocyclic carbenes. These carbenes are highly stable, as I said just now, over the Fischer and Schrock carbenes because of the 2 interactions here, that is push-pull interactions. So this is the imidazolium core given here. These are the 2 nitrogen atoms. They are having a completely filled orbitals, right? Completely filled non-bonding orbitals. While this carbene-carbon is having an empty orbital. These are considered as singlet carbenes, and the last 2p orbital is empty in this case. So this lone pair of electrons from the nitrogen atom, which is attached adjacent to the carbene-carbon, is given away the electron density to the empty p orbital of the carbene-carbon. On the other hand, nitrogen being more electron negative than carbon atom, it pulls the electron density from the carbene-carbon. So these are 2 interactions, means pulling up of unpaired electrons or non-bonding electrons from the nitrogen to the empty orbital of the carbene-carbon, and pulling the electron, shared pair of electron density because of the higher electronegativity value of nitrogen stabilizes the entire molecule. So these N-heterocyclic carbenes are slightly stable over Fischer and Schrock carbenes, but you cannot find this type of push-pull interactions in both the cases. Further, the electronic stabilization is possible in case of imidazolium salts, since imidazole core is an aromatic system. Imidazole core is an aromatic system. Electronic stabilization can happen within the ring system, and push-pull interactions collectively stabilizing the N-heterocyclic carbenes. Now, in 1960s, Vanslick and Shikora, these were the first people, means in 1960s means around 80 years ago. So these are the people who have worked on the isolation of the free carbene. So this is imidazolin derivative, which is having trichloromethyl substitution at the second position of azolium system. So when they thought that if they heat this molecule at 150 degrees Celsius, so H and trichloromethyl substituent comes out in the form of chloroform, and that generates a carbonate C2 carbon atom. This is considered a C2 carbon atom 1, 2, 3, 4, and 5. So a carbene was generated at the second position. Unfortunately, that eventually led to the formation of a dimer. Means these two compounds, means two of these carbenes dimerized to form this kind of a dimer, and this dimer is in equilibrium with the carbene, but it's not 100% pure carbene. These carbenes are in equilibrium with the dimerized product like this way, and this equilibrium is called as Vanslick's equilibrium. To isolate the free carbene was unsuccessful until the Ardingo's free carbene isolation in 1991. Actually, this NHC chemistry actually got birthed in 1991. So it's about around 30 years old chemistry. Right? This is just 30 years old chemistry. Now, so in 1991, 1,3-diadabentyl imidazolium chloride was treated with a strong base such as sodium hydride in THF at this particular catalytic condition. Then they could able to isolate the free carbene. They could able to isolate the free carbene here, so which is of course air and moisture sensitive. But still, free carbene can be isolated. From there onwards, many efforts have been taken place in order to isolate the free carbenes, but still they are reactive. Stable singlet carbenes and their synthesis. Way back in 1960, the same thing happened. The Vanslick equilibrium, he could not able to isolate the free carbenes. While in 1991, with the help of strong bases, like how I said just now, so few people could able to isolate these free carbenes. While in 1993, a full-fledged carbene isolation procedure was established by Kamm, who's a kind of German scientist. So that is having thion, imidazole 2 thion derivative upon treatment with metallic potassium forms K2S, and that generates a carbene here, and these carbenes are quite stable. While in 1995, it seems, Yender worked on triazolium salts, triazolium derivative. This is 1,2,4 triazolium derivative, which is having a methoxy substitution at 5th carbon atom upon treatment with again a strong base at little elevated temperatures. Methanol is a byproduct here, and they could be able to isolate the free carbene. So these are room temperature stable carbenes, but yet reactive towards moisture and atmospheric air. Later on, many people have tried to isolate the free carbenes, which are donor functionalized one. For example, in this particular case, this is a chiral carbene derivative, which is having the azoxazole derivative. So similarly, phosphorus functionalized carbenes have been isolated. So supports carbenes with supports such as polystyrene, right? So these molecules have already been isolated. Similarly, zwitterionic compounds have been isolated, and bis NHCs have also been isolated. Well, these are the stable NHC complex NHCs that have been reported so far, and we could able to review all these things in these review articles and few synthetic articles, few research articles as well. So these are the stable NHCs, and on the right hand side you can find the chiral and heterocyclic derivatives as well. So which are composed of the cores like imidazolines, imidazoles, triazoles, like benzimidazoles. These carbenes are having varieties of substitutions. The next thing is the catalytic applications. We have seen so far the basic aspects of N-heterocyclic carbenes, and what are the applications of these carbene complexes. See, in catalytic applications are well endorsed in the literature. So for example, Grubbs catalyst, of course, Robert H. Grubbs, who's Nobel laureate in 2005, along with Schrock, Richard Schrock, he got the Nobel Prize in 2005 for fantastic discovery of olefin metathesis catalysis. So Grubs, if you look at carefully the structure here, unstable, right? During the catalytic process, this particular system is highly unstable because the ruthenium center is not stabilized by any of the strong field ligands, right? Though it has one carbene ligand here, but this was not stable enough to maintain the active species life for a longer time. While later they have changed one of the triphenyl phosphine ligands by a carbene ligand. This is imidazoline ligand, which is having mycidyl substitutions on either side of the nitrogens. So though this catalyst is stable for a long time during the catalysis, but its activity is not that improved. Activity remains same, but stability is increased. So in order to, and this is considered as the second generation Grubs catalyst. While in order to increase the catalytic efficiency or efficacy of the ruthenium catalyst, they have introduced a pyridine ligands, two pyridine ligands instead of triphenyl phosphine ligands, aside tricyclohexyl phosphine ligands. These pyridine ligands have been introduced, and these are considered as throwaway ligands, which facilitates the ruthenium to bind with the substrate easily. So this particular catalyst has given improved activity as well as improved stability, and this particular catalyst is still found in the industries, and it has vast industrial application in olefin metathesis reaction. Alongside, palladium complexes, right, have been extensively used for cross-coupling reactions. This is one part of the catalytic applications of carbenes. Second part is catalytic application, that is homogeneous catalytic applications, in which boronic acid, phenylboronic acid, is a coupling partner with aryl halides to form CC coupled product, right? So again, in 2010, this particular field of chemistry received Nobel Prize. Akira Suzuki, Richard Hack, and Ichi Nekeshi, right? So because of their pioneering work on palladium catalyzed cross-coupling reactions in organic synthesis. Now, my research work is a combination of these two things. We have got something about the NHC stabilization from the Grubs catalyst, and palladium source is an active catalyst for the CC coupling reactions, right? So on these grounds, we have designed our ligand systems. On our ligand system, why NHCs are so used or to be given more focus or prominence, because the R substitutions, R1 and R2, that are on the nitrogen atom can be fine-tuned. So these we call them as wingtip substituents, and these wingtip substituents can can be donor functionalized. So with the help of a donor atom here, which can be coordinated to the metal center in order to increase the stability of the compound. So these NHCs can be fine-tuned at nitrogen atoms in order to receive the steric and electronic requirements around the metal center in case of the complex form. So fine. Second objective of using N-heterocyclic carbenes is the feasibility or possibility of altering the backbone substitutions here. So this is called C4 and C5 carbon atom. So there is a chance that you can alter the electron donating or electron withdrawing groups here at the backbone of the azole ring, which can indirectly affect the donor strength of the NHC. So through which you can control the steric requirements or electronic requirements around the complex resulted, which indeed effective for the catalytic applications. So these N-heterocyclic carbene complexes can be fine-tuned in order to get the appropriate lipophilicity in biomedical applications, appropriate biocompatibility, and increasing drug potency. So many of the drug molecules are having NHC complexes, NHC ligands. So further, the catalysis has also evidenced many of the NHC donors in which steric bulk can be easily altered by either R1 substitution or R2 substitution. Steric bulk can be easily altered, and electronic environment of the metal center can also be fine-tuned with the help of backbone substitutions or the substitutions that are present on the wingtip group. So because of these flexibility, we have designed our ligand system this way, right? So we have an alkyl group here attached to the nitrogen atom of the triazole ring system. This is 1,2,4 triazole ring system. We are having an alkyl group. Alkyl group is ranging from methyl to N-hexyl and a benzyl substitution. So these are the these substitutions are having sp3 carbon atoms, and we know that these sp3 carbon atoms are having free rotation around themselves, which provides appropriate steric bulk around the metal center. Metal center is formed here, right? Upon the coordination of the lone pair of electrons, a complex is formed here, and this metal is having appropriate steric bulk around it. So that can be fine-tuned by changing the wingtip substitutions or alkyl group substitutions at this particular nitrogen atom. At the second nitrogen atom, we thought that let us have one more donor group, something like a allelic protons. So this particular proton is allelic protons. Directly we can have the allyl substitution here, which is having a proton, but deprotonating an allyl proton is highly difficult since it is highly aliphatic in nature. So instead of that, we have gone with the coumarin substitution. This is 4 substituted coumarin, 4-bromomethyl coumarin, which is having a proton atom, a third carbon atom, which is slightly basic in nature. So because of the presence of this allelic nature, because of the presence of this allelic substitution, C3 of hydrogen is slightly basic, and if we could able to deprotonate this, a carbanion is generated at C3 carbon atom of coumarin, which can be coordinated to the metal center. So here it is, the combination of triazole, which is having a carbene carbon atom in it, and counter at C3 position of coumarin, we have a proton. So these two can be deprotonated with the help of a base, with the help of a strong base, so that a carbanion is generated here and a carbene is generated here. These two can coordinate to the metal center this way. In order to form a chelate. So this is something like cyclometallated derivative. Wherein carbene coordination is possible from azole, and a carbanion coordination with something like a cyclometallation coordination possible from this carbon to the metal center. And around the steric, this metal center, steric bulk can be altered by changing the alkyl groups here. So this is the actual present NHC design. In this we have synthesized azolium derivatives, means triazolium derivatives. We have synthesized several triazolium derivatives with this combination, right? With this combination, this is right. It's fine. This is triazole, means 1 alkyl 1,2,4 triazole. This is referred as 1, 2, 3, 4, 5. 1 alkyl 1,2,4 triazole, which is prepared using the established procedures. And this 1,2,4 triazole, alkyl 1,2,4 triazole, was treated with 4-bromomethyl coumarin, which is having some electronic substitutions or some substitutions at the backbone of coumarin phenyl system. So this particular reaction is considered as the salt formation reaction, and we will end up with this particular salt. This is something like what I have shown in my first slide, that is imidazolium salt. So now we have coumarin substituted. Now we have coumarin substituted 1,2,4 triazolium salt. So this coumarin is having a weak or fragile hydrogen atom here that can be deprotonated. Initially we thought that this can be deprotonated, and a carbene is generated at the C5 carbon atom. So this is considered as 1, 2, 3, 4, and 5. At 5th carbon atom, a carbene can be generated and a carbanion can be generated at C3 of coumarin, so that these two can coordinate to the metal center. In that we have designed this ligand system, and these bromide salts were subjected to salt metathesis with the help of potassium hexafluorophosphate to get PF6 salts. So these PF6 salts are highly stable because of the presence of 6 fluoride ions here. The molecule can be involved in extended hydrogen bonding interactions, so that we will get the solid crystals of this. So with that intention, we have prepared the PF6 salts, nothing else. We are not using these things for any of the reactions. We will go ahead with the bromide salts of triazolium systems, right? So for these bromide salts of the triazolium systems were treated with palladium acetate in DMSO at 90 degrees Celsius for 24 hours. We were expecting this kind of complex formation, that is carbene is generated at C5 carbon atom, followed by a carbanion generation at C3 of coumarin, which are trapped by the metal center, and rest two coordination sites of the metal were satisfied by the acetate anion, which also acts as a binding ligand. Unfortunately, this was not the structure of the molecule we got. Instead, we got something like bis NHC coordinated palladium complexes in transposition, right? So this is the eventually formed a complex. That's because of the steric bulk. This is not formed because of the kinetic stabilities or kinetic restrictions, thermodynamic restrictions. We were ended up with the bis NHC coordinated palladium complexes, which are square planar in nature and trans geometry, right? So these salts and complexes were obtained in high yield, that is 92 to 95% yield. Salts and complexes were appeared in 72 to 83% purity, 83% yield, and complexes were purified by column chromatography before they are subjected to further analysis. Next, initial characterization, since audience, BSc students or master students may also be present. Let us have, that's the reason I've included NMR spectral characterization here. Otherwise, I would have not included this. So let us understand the NMR spectroscopic results of this particular salt. This particular salt is having C5 proton. The one that is represented in blue color is C5 proton. The one that is in red color is C3 proton. These two are the most acidic protons. These are the two most acidic protons, and these were resonated at 9.2 and 10.17 respectively, delta ppm, right? So this is because this particular proton is highly deshielded due to the presence of two substituted nitrogens attached to the carbon atom, while here this nitrogen is substituted but not the other nitrogen. So because of that difference in the deshielding process, C5 proton appears at 10 and C3 proton appears at 9 usually, and this is well matching with the literature data as well. So the rest of the proton resonances are in accordance with what we have expected. Similarly, carbon NMR is also recorded for this particular salt. This is having 4 alkyl substitutions. One is here, second, third, and fourth. These are the 4 alkyl substitutions, while rest of these are the aromatic protons, in which coumarin is having signature peaks that is around 160, 150, and 148. So these evidences that the salt has been formed. Further, this is the particular complex. I've just illustrated one of the NMR spectrum, one of the NMR spectra of palladium complexes here. This is corresponding to palladium NMR spectra. Now, this spectra is, we don't have any peak around 10. See, organometallic compounds are well characterized with the help of the NMR spectroscopy, because we have at least one carbon to metal linkage. So metal is considered as highly electropositive, so that it drags all the electron density from carbon atom. So whereas in salts or in ligands, carbon is organic carbon, while in the complex, so it turns out to be carbene, and the electron density has been removed from this particular carbene, and this has to be deshielded and appears way downfield region, right? So there is, in the proton NMR spectrum of this particular complex, there is no peak corresponding to C2 here, C5 proton. See, this is C5 proton that is appeared at 10.1, whereas in the complex, there is no proton appeared at 10. There is no proton appeared at 10, indicating that this proton is deprotonated and the carbene is generated, which is trapped by the metal center. So that is how we can isolate here. That is what the inference we can draw from this particular NMR spectrum. C5 proton is deprotonated. Through deprotonation, a carbene is generated. That deprotonation is appeared here. There is no proton resonance appeared at 10 ppm. Further, all these peaks, all resonances corresponding to proton are in duplicates. Each and every resonance proton here, resonance of the proton resonances are appeared as sibling peaks. This sibling peak appearance is due to the dynamic behavior of the palladium complex in solution, which is attributed to the formation of rotamers. So this is a trans anti-rotamer, whereas this is a trans syn-rotamer. Look at the arrangement of NHC ligands around the metal center. Look at the NHC arrangement around the metal center. So these two substituents are opposite to each other. So we call this as a trans anti-arrangement, while here both the coumarins are on either side of the palladium center. And these two alkyl groups are one side of the palladium center. This is a trans, of course, syn-rotamer. So this is syn anti. Because of the existence of this equilibrium, we are supposed to get sibling peaks for each proton resonance. Similarly, carbon resonances are also doubled here. In the carbon NMR spectrum, carbon NMR resonances are also doubled because of the rotamer formation. Fine. So this particular carbon resonance is 135 in the carbon NMR of this salt, while in the complex case, so we could see a resonance appeared at 171. Whereas in the salt, there is no 171 spectrum, no 171 resonance. And this could be attributed to the resonance of carbene-carbon, which is attached to the metal center. Because of the electropositive palladium center, because of the electropositive metal center, this carbene-carbon is deshielded and appeared at 171 ppm. These are the two indications that one can easily say the successful synthesis of the palladium complexes. And this particular NMR pattern explains us that the rotamers are possible in the solution. Further, single crystal XRD analysis has been done. Single crystal XRD analysis have been done using these salts. So we could able to get the single crystals of 3 salts here: salt number 7, 9, and 11. Salt number 7, 9, and 11. So these crystal structures clearly illustrate that the salts have been formed anambiguously. Similarly, complexes were also obtained in crystalline form and solved for their crystal structures. So this is the particular crystal structure of a complex that is 13, which is having ethyl substitution and coumarin substitution on either side of the triazolium system. So this is the three-dimensional structure. This is the another complex, right? Another complex that is also having trans-anti arrangement. This is confirmed by the solid state analysis. XRD analysis is solid state analysis, so that unambiguously we can believe the structural elucidation. So this is trans arrangement because these ligands are trans to each other. Both NHC ligands are trans to each other. Bromido ligands are trans to each other. And coumarin arrangements on NHC on opposite side of the NHCs, on the opposite sides of both the NHCs. This confirms the trans-anti arrangement. And because of the presence of electron density in the coumarin substitutions, so stacking interactions are possible. So these are the stacking interactions of the same complexes. Similarly, we could able to get the crystal structure solved for butyl substituted NHC palladium complex and benzyl substituted palladium NHC complex, and all these complexes have displayed stacking interactions, pi-phase stacking interactions. Further, all the complexes have already been studied for, have also been studied for the structure using CHN elemental analysis, and the results were in well agreement with the calculated percentage of DCHN percentage. Further, we have changed the strategy to get what we were intended to get, this kind of complex formation, but that was not possible again. But we got a product which is not having C3 proton, neither C2 proton. We got a product. So what is the change in the synthetic strategy now? That the reaction was carried out in pyridine. We thought that this pyridine is sufficient enough to deprotonate C3 proton of coumarin and C5 proton of triazole. So the product what we got, we have analyzed it for proton NMR, and proton NMR says that there is no peak corresponding to C3 of coumarin and no peak corresponding to C5 of triazole. So we thought that this particular complex is formed, but its X-ray analysis helped us to establish the exact structure, which says that this is not a complex form. Instead, that has given some organic transformation. So this is an organic transformation considered as crossed dehydrogenative coupling. For example, this hydrogen and this hydrogen have been dehydrogenated, and the carbene-carbon, which is formed at fifth carbon atom of triazole, and C3 of coumarin are coupled together. So that is a new bond formation here. This resulted in the formation of a fused triheterocyclic system, which is having coumarin, pyrrole, and azole system as well. So our efforts did not follow this. Our efforts did not give this one by changing the palladium, by changing the solvent, that is strong base pyridine. While in the other case, we could able to get again this kind of complex formation. That is a triazole on one side, bromidos are there, but on the other side of the complex we have pyridine, since we have used the pyridine as a solvent. Your solvent itself is pyridine, so we did not get this kind of complex formation, while we got this particular type of complex formation, right? And this is called pyridine enhanced precatalyst preparation, stabilization, and initiation. Now these things were again further characterized by IR and NMR spectroscopic techniques. Now we have used all these complexes. As homogeneous catalysts. In Suzuki cross-coupling reaction. In the introduction, I have already explained what is Suzuki cross-coupling reaction. We have a phenyl boronic acid as a coupling partner, along with aryl bromides. In the presence of a particular base solvent and appropriate time of the reaction, in the presence of a palladium catalyst, it forms a coupled product. Right? CC coupling reaction. These are industrially useful. So these are the several drug-like molecules being prepared in the industry by following a PD catalyzed reactions. So this is our catalyst optimization using complex number 18, which is evidence that potassium carbonate is an appropriate base here, toluene is an appropriate solvent. Reaction was ran for 4 hours in the presence of this particular catalyst. That has given us 85% conversion. That has given us 85% yield. So by keeping this thing, we have studied the substrate scope. We have changed the substrates here, coupling partners, substituted coupling partners. And finally, we could able to get, in this particular case, yield up to 84%, 87% in few cases with respect to bis NHC coordinated complexes. while mono NHC with the pyridine substitution, we could able to get somewhere around 96% yield here. Further, the same complexes have also been evaluated for the CH activation catalysis. Means this is a cyanopyridine derivative which is having thiophene substitution. So this thiophene substitution can be arylated at C5 of thiophene with the help of an aryl halide in the presence of these palladium catalysts. So this has given us this direct arylation using these palladium complexes has given us 97% yield, especially in the case of pyridine coordinated complexes. And this is the starting material preparation. Now we have studied the substrate scope here. So we have changed the R substitution. Methoxy is there, methyl substitution is here. So these organic derivatives can be synthesized with the help of these palladium catalyzed direct arylation reactions or CH activation reactions. So we could able to get the conversion or this product formation in the range 92 to 97%. We got the complex isolate, means the product isolated 97% yield with the help of these palladium catalysts. Of course, if you look into the structure activity relationship, these complexes have given lesser yield, say suppose 62 to 72%, while the pyridine ones have given yields up to 97%, 92 to 97% yield. This is because of the structural changes possible or structural differences in these two compounds. See, here we have a pyridine ligand, so which is easily decoordinated. We call this as throw-away ligand. Because of the presence of throw-away pyridine ligand, yield is rather increased here. The summary of this particular palladium complexes is a series of palladium bis NHC coordinated and peptide themed palladium complexes have been prepared, which are having NHCs substituted with coumarins, and all the characterizations were done using spectral and elemental analysis. Solid state structures were established, right, using single crystal X-ray diffraction technique. So it is evident that in the both in CC coupling, Suzuki-Mehra cross-coupling reactions, as well as in the CH activation reactions, Pepsi-themed complexes have evidenced better activity than the bis NHC complexes. That's because of the presence of labile pyridine ligand. We could be able to publish this work in New Journal of Chemistry and Journal of Organometallic Chemistry. Next is something different than what we have seen just now, that is half sandwich nickel complexes, of course, of the similar ligand design, and the application of these ligands or complexes is totally different. So we have now we were the first people to report these nickel NHC complexes as glucose sensors for the first time, right? So these complexes were used as glucose sensors, something like what diabetic people use to check in their glucometer. So glucometer is attached with a strip that is loaded with a glucose oxidase enzyme. That's a biosensor, glucose oxidase enzyme, which can detect the amount of glucose present in the blood samples. Difficulty with the glucose oxidase enzyme is its poor electron transfer between FAD. That is, this is the active species present in that flavin adenine dinucleotide and the electrode material. So because of the poor connectivity of glucose oxidase enzyme, it's all the time, it's not actually the same glucose content present in the glucose in the blood samples. Many of you must have already experienced it. Of course, those who are diabetic, so if they check the glucose content with two different strips using a glucometer, the reading will not be same. Reading will not be same. That's because so accurate detection of glucose is not possible with the help of glucose biosensor, that is glucose oxidase enzyme. That's because this particular enzyme can undergo denaturation with respect to rise in temperature and with respect to rise in pH level. So that's the reason one cannot able to get the exact glucose concentration in the blood samples. So that's the reason people have already established some non-enzymatic glucose sensors. Non-enzymatic, there is no enzyme content here. Instead, we have a chemical molecule which can sense the glucose. So we call them as glucose sensors. So these nickel NHC complexes, what we have prepared, have been evaluated for the glucose sensing ability using electrochemical methods. And we could be able to get this paper published in Biosensors and Bioelectronics, which is one of the premium journal, we would say. Next, synthetic strategies, synthesis of NHC precursors. This is almost the way how we have seen in the palladium case. Right? So instead of alkyl substitutions here, we have aryl substitutions. That is mesithyl substituted imidazole system is here. Along with that, a coumarin substituent. Again, we have expected the involvement of C3 of coumarin, but that did not happen. So we have prepared, so here we have, in the previous case, we have this methyl substitution there, but in this case, we have electronically modified the coumarin substitution, that is methyl group is there and chloro group is also there. Similarly, we have also prepared a sterically varied ligand system, that is 7-8 benzocoumarins, and means these are benzanulated coumarins, 7-8 benzanulated coumarin and 5-6 benzanulated coumarins. So these two variations can give us the electronic modulation in the metal center, while these two modulations can give us the steric modulation around the metal center. Okay. So complexes as prepared, means nickel complex is prepared this way, means the salt was treated with nickelocene. Nickelocene is just like ferrocene. This nickelocene was treated with this salt in the presence of in THF under the nitrogen atmosphere under the Schlenk technique. So in order to get this particular type of complex, so this is a half sandwich complex. Ferrocene is a sandwich complex. Even nickelocene is a sandwich complex because nickel is sandwiched between two planar cyclopentadienyl ligands. Nickel is sandwiched between two cyclopentadienyl ligands, while here nickel is present with only one CP ring, hence this is called half sandwich derivative, right? Nickel half sandwich complexes. So along with that, there is a bromido ligand. Along with that, there is a bromido ligand and a carbene ligand here. So these particular complexes are electronically modulated, and these two particular complexes are sterically modulated. These two particular complexes are sterically modulated, and both the salts and complexes were collected in good deals, high purity, and complexes were purified through column chromatography once they are purified. Again, in brief, I would like to explain here the NMR spectroscopic results. So salt is formed here. Salt is formed here, Dr. Shashikant sir. Please mute your mic. So please mute the mic, sir. So this is the azolium salt evaluated for proton NMR. So C2 proton is the most acidic proton of the system. We got this around 9.5 ppm. 9.5 ppm. Rest of the resonances are in accordance with what resonances we are expecting from the protons of the salt. Well, this is the complex NMR spectrum. Look at the peak around 4.5 delta ppm, so which is corresponding to the protons of CP ring, which confirms that CP is coordinated to nickel. Further, representative salts and nickel complex have already been evaluated for their structure by single crystal X-ray diffraction technique. A salt is present here. This is having mesitile substitution, imidazolium, with a chloro-substituted coumarin derivative, and pi stacking interactions. Similarly, salt 12 is crystallized in two crystallographically different but chemically same entities. Chemically they are same, but crystallographically small differences are. So this is about differences are there. This is about the crystal structure of salt 12, which is having mesitile substitution, imidazole, and 7-8 benzanulated coumarin. So this gives the steric variation around the metal center, while this is believed to provide the this is electronic variation around the metal center, while this is believed to provide the steric variation around the metal center. Well, this is the X-ray crystallographic structure of nickel complex. You can clearly see that this is the CP ring, and all the 5 carbon atoms of the CP ring are connected to metal center. Along with that, a bromido ligand. So this is the NHC ligand system. And these complexes have evidenced pi stacking interactions and extended hydrogen bonding interactions, which stabilize the molecule. So this is about the characterization of the molecule using single XRD. We have analyzed this material. See, we have these materials have been drop casted on the glassy carbon electrode, right? Electrochemically, we want to evaluate the glucose sensing application of these complexes. Hence, these complex solutions have been drop casted on the surface of the glassy carbon electrode, which is working electrode in CV experiments. Hence, we need to understand the morphology of these complexes. So for that reason, complex number 16 was evaluated for its morphological studies. And interestingly, we could able to find a highly porous structure with honeycomb-like morphology, in few micrometers. Right, in few micrometers, whereas the other one is an agglomerated structure, which is ignored. So these two compounds have given highly porous honeycomb-like morphology, which helps to interact with the glucose substrate, which is present in the blood samples. Next, electrochemical glucose sensing or detection was carried out. Means this was done using a CV technique, cyclic voltammetric technique, which is having a typical 3 electrode assembly, in which AgCl electrode acts as the reference electrode and platinum acts as a counter electrode, and the working glassy carbon electrode, so which is modified with the complexes. We have 4 complexes here. These 4 complexes were modified. These 4 complexes were modified. For example, 15, 16, these are the 2 complexes, 17 and 18. These are sterically modulated and electronically modulated complexes, nickel complexes, were drop casted on 4 glassy carbon electrodes, and with the help of CV technique, these have been studied for glucose detection, right? So with that 3 electrode assembly, working modified, complex modified working glassy carbon electrode, HEGCl, and platinum electrode. So in the electrolytic solution, the red one, there is no glucose content there. It is just sodium hydroxide solution. As the glucose concentration was increased in the electrocatalytic cell, in the electrolytic cell, the peak currents, means oxidation peak currents corresponding to nickel, has been increased. So for example, here it is hardly we could find 10 micromoles, hardly we could find 10 microamps of current density in absence of glucose, while upon addition of the glucose, the 142.5 micromoles of glucose, the current density was increased more than 10 times. We could able to get around more than 100 microamps of current here. Right, more than 100 microamps of current here. This is because of the electrocatalytic oxidation of glucose using nickel modified electrodes, using nickel complex modified electrodes. So in the first case, we got current density up to 100 microamps, whereas in the second case, it has gone over 200, close to 250 microamps. While in the third case, we got a maximum one, that is around 320 microamps of current at 142 micromoles of glucose. While in the third case, it is while in the last case, it is the least active. This is the least active one. So activity of these nickel complexes is in this order. 17 complex number 17 is the most active one, which is 16 is slightly lesser than that, 15 is slightly lesser than that, and 18 is the most least active one, right? So these activities, this emphasizes that complexes can be used as glucose sensors, that to non-enzymatic glucose sensors. Further, we have studied the calibration plot sensitivity of the electrodes, lowest detection limit of detection, glucose limit of detection. So using chronoamperometric techniques. So chronoamperometric technique is a time-dependent addition of glucose into the electrocatalytic cycle with the increasing amount of glucose concentration. So with the help of these techniques, one can easily identify the sensitivity of the electrodes, which is quite high. All these electrode materials have shown high sensitivity in the range of 9,000 to 28,000 microamps per millimoles of glucose per centimeter square. So with the help of this, one can easily identify the unknown concentration of the glucose present in the blood sample. This is like how we do the unknown concentration of copper solution using B. Lambert law, right? So in a similar way, one can easily identify the amount of glucose present in the blood samples, and the least amount of detection, or the limit of detection of these complexes, is somewhere around in 1 point, or maximum is 2 micromoles. Even you can identify 2 micromoles of glucose in the blood samples. Just 2 micromoles. 2 micromoles. In blood glucose level, it's up to 6 to 8 millimoles, 6 millimoles. While we could able to identify even this less amount of glucose present in the blood sample, means they're highly stable and sensitive, highly sensitive. Fine, we have also studied the effect of other blood constituents. That is, when once the glucose is added, there is a response, there is an increase in the current. While the other blood constituents, such as ascorbic acid, uric acid, and dopamine, these are also present in the blood sample. But this particular sensor, means the modified electrodes, have not given any response towards ascorbic acid or uric acid or the dopamine. There is no response actually. But with the addition of glucose, it gives a sudden increase in the current response, which indicates that these complexes are actually glucose sensitive. So similarly, we have added glucose first. We got the sensitivity, means glucose can be detected, but not the other blood constituents. We have done the same same experiment in around the five, right? So wherein ascorbic acid is added first, no response actually, even the current is decreased. Uric acid, no response. Dopamine, no response. While at the end, if we add glucose, yes, there is a current increase, right? There is an increase in the current response that indicates that so these complexes can selectively bind to glucose or selectively identify the glucose. So on these grounds, we have just predicted the plausible mechanism, right, of how glucose is sensed by these molecules. This is through the oxidation and reduction process. This is the complex actually which is modified on the glassy carbon electrode. Nickel 2 undergoes oxidation in the presence of undergoes oxidation to form nickel 3 with a hydroxyl species. So this enters the catalytic cycle, and again glucose is oxidized to glucolactone, while nickel is reduced to nickel 2. So this is the possible mechanism. Similarly, we have changed the synthetic strategy here. We have changed the synthetic strategy in order to get a few more substituents here to get more sensitive or more effective glucose materials, So these two particular complexes were also being prepared in order to tune the morphology. These substitutions are varied in order to tune the morphology as well as the sensing ability. So here we have ended up with the 4-coordinated nickel complex, which is established by the single crystal X-ray diffraction technique, and these are the morphological studies. So this is almost in the nanoscale. This particular complex is appeared in almost nanoscale, and this is a globular structure. This is granular structure. We call it as nanogranular structure. So these are we got these things from FASM analysis. Further again, these complexes were evaluated for the glucose sensing application. Herein, these two complexes were blended with 10% of mesoporous carbon and 20% of mesoporous carbon. So this is the interior one is just a nickel complex, while these two are the composites of nickel and carbon material. And because of the presence of mesoporous carbon, the current responses are almost threefold increased here, right? So it's not, this particular observation inferences that it's not just nickel complex which is sufficient for the electrocatalytic glucose sensing. Instead, if we have supporting materials such as carbon materials, that gives you better results. So these are the electrocatalytic glucose sensing applications, the way how we have done, how I have explained just now in the previous case. These are the chronoamperometric techniques, right? These are the chronoamperometric techniques. Here one can easily identify the glucose up to 25.5 millimoles. So for a healthy person, the glucose concentration in the blood samples is around 6 millimoles, 4 to 6 millimole, while one can easily identify the glucose concentration of up to 27.5 millimoles of glucose using these complexes. 27 millimoles. Hyper glucose concentrations can also be measured accurately using these modified complexes. Further, we have done the stability studies here. The catalyst was studied. Now, this particular catalyst was stable up to 18 days. So this is the first day, the black colored one is the first day chronoamperometric response. We have kept the electrode as it is, modified glassy carbon electrode, and we have ran the same experiment, that is chronoamperometric response. After 18 days, still the material is stable enough. Similarly, we have done the interference studies here, ascorbic acid, dopamine, uric acid, and sucrose as well. So when the addition of glucose, it gives a drastic increase in the current response. While though the current response is here, that's very negligible. At the end, again, if you add glucose, again it shows sensitivity here. It means these particular nickel complexes are active towards the determination of glucose, even in the presence of other blood constituents such as sucrose, uric acid, dopamine, and the ascorbic acid. So this is about the impedance spectra of the modified complex. It's not relevant, I believe. So this is about the summary of the work. So we have prepared half sandwich nickel NHC complexes, a series of nickel NHC complexes. Those were evaluated by the spectral and analytical techniques. Crystallographic structures were already been established. And these complexes were found as effective glucose sensing materials because of their robust honeycomb-like morphology and readily evolved as nickel hydroxyl species of the complex. These are intermediates actually. And finally, these can be used as effective glucose sensing materials because they are selective towards glucose, even in the presence of other blood components like what I said as ascorbic acid and uric acid. So this is about the nickel NHC complexes and their electrocatalytic application. And this is the first ever now report on nickel NHC complexes or nickel organometallic complexes being used for electrocatalytic applications. Dr. Shashikant? So shall I conclude, sir?
Hello, sir. Hello, sir.
It's 1 hour done, sir. 1 hour is up, right?
Yeah, sir.
Okay.
Hello, sir.
Yes, sir. 1 hour is done, right? I'm not left with any
Yeah,
more time.
yes, sir. Now you have to stop, sir.
Okay. Fine. Actually, I was having few more things here.
Sir,
Finally,
you can take 5 more minutes, sir, if you want to.
no, I'll just wind up this by acknowledging the people. So I would like to acknowledge or thank my host university, that is Jain University, Bangalore, because of the infrastructure facility, Department of Science and Technology for the financial support through Young Scientist Grant. Dr. D.H. Nagaraju, who is associate professor in Reva University, helping me out with electrocatalytic applications. Jan Melaki, who is my collaborator in Poland, who has solved all orchestral structures here. Director Madam, CNMS Jain University. And I thank all my present and past PhD and master students. And finally, I thank the organizing committee of this particular international webinar and all the audience. Thank you so much.
Thank you, sir. Thank you for your wonderful informative information on the organometallics in catalysis. Thank you, sir. On behalf of our management, our college, I would like to thank you very much, sir.
Thank you so much, sir. Thank you so much. Have a nice day. Thank you so much.
Yes. Now we will move on to the fourth session. Topic: how does nanoscale light look like? Delivered by Dr. Rohit Chikreddy. Before delivering his lecture, I would like to introduce about him. Dr. Rohit Chikreddy. He has done PhD Physics, University of Cambridge, UK. Dr. Manmohan Singh Scholar at St. John's College, fully funded competitively, won scholarship from British Council, and he has completed BSMS dual degree, Indian Institute of Science, Education and Research, Pune, India, and he also received KVPY Fellowship, students for UG Research DST India, and he has completed 12th standard in 2009, Jawahar Navodaya Vidyalaya, Kukanur, Koppal, Karnataka. Currently, he has a position as a research fellow, Trinity College, University of Cambridge, UK. On 2008 onwards, he is working as an independent research position at the Department of Physics, University of Cambridge, UK. He has also received some fellowships and awards. Best Oral Presentation Award at Single Molecule Sensors and Nanosystems International Conference, Munich, Germany. In 2016, he has also received Inquisitive Mind Award at Gordon Research Conference on Plasmonics and Nanophotonics, Newry, ME, USA. In 2016, he has received Bayer Lindau Fellowship, Lindau Nobel Laureate Meeting as Young Independent Researcher. And he has also received Academic Excellence Award twice for exemplary performance at ICER Pune. In 2014, he got a Best Poster Award for Master Thesis work presented at National Science Day. He has also got Summer Research Fellowship, Summer Internship at Notre Dame University, USA. And he has also got Silver Medal at Asian Science Camp held at Korean Advanced Institute of Science and Technology, South Korea, participated by more than 21 countries. He has also received BASF Appreciation Award for their best ideas on role of the chemical industry
to enhance the quality of education and research in India. In 2009, he has also received National Initiative on Undergraduate Science Fellowship, research internships at Tata Institute of Fundamental Research, TIFR, Mumbai, India. He has also received 2007 KVPY Fellowship, a prestigious UG Research Fellowship from Department of Science and Technology, India. And he has also published a number of articles, more than 40 international articles. Also, he has a H index 18, and he is also currently working as a referee for peer-reviewed journals like Nature Review Physics, Nano Letters, ACS Photonics, Optics Express, Advanced Optical Materials, Advanced Quantum Technology, Nanoscale, Advanced Materials Today, Nanoscale Method, Material Origin, etc. Sir, with this brief introduction, I welcome to Dr. Rohit Chikreddy. He has presenting his topic, how does nanoscale light look like? Sir, please. Hello, sir. Ah.
चिकलड्डे आपला मीटिंग आहे म्हटलं 8 म्हणतात तर
ಇದಾದ್ರೆ
ಬರ್ತಾರೆ. ಅವ್ರಿಗೆ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡಕ್ಕೆ ನಾನು ಅಲ್ಲಿ ಪಿನ್ ಮಾಡ್ತೀನಿ.
Hello, sir. Sir, your voice is not audible. Sir, please press the mute button. Hello, sir. Are you audible? Sir, are you audible? Sir, are you audible?
ಸರ್ ನೀವು ಮಾತಾಡಿ ಅನ್ಮ್ಯೂಟ್ ಯುವರ್ ಸೆಲ್ಫ್ ಅಂತ ಹೇಳ್ರಿ.
Sir, sir, please unmute yourself, sir. Sir. Hello, sir. Sir, are you audible? Sir, unmute yourself. Oh.
Can you hear me? Is it clear now?
Yeah. Now I am audible your voice. Sir, now are you audible my voice?
It should go.
Rohit, sir.
Can you hear me now?
Yeah. Now, yeah, sir. And share your PPT right now. No, I am not receiving your voice.
Am I audible?
Yeah. You are audible, sir. So proceeds. So share your screen. Yes.
Excellent. I hope people can hear me. And let me start by thanking for a very kind introduction. It's very nice of it. And also, I take this opportunity to thank the organizers to putting together this wonderful seminar. It's very well organized. It's very nice talks. I have been enjoying these talks in the last 2 days. So what I'm going to do today is I'm going to discuss some interplay between vibrant colors that we see in nature and how they play a critical and important role in our day-to-day life. I hope all of you can see my slide. On this background, I have put a photo that was taken at Kemangundi during my last visit to India. What I want all of you to focus on in this picture is there are 3 vibrant colors. Green, obviously, from the plants, and blue from the sky. And there is also a small little white shade on the right side of my screen coming from the clouds. What is interesting fact about it is these 3 colors have a completely different origin. Chlorophyll in plants absorb red and blue light from the sun, and what we see is a complementary green color. Whereas sky looks blue, predominantly blue, because of the scattering by very small molecules, nitrogen and oxygen in the atmosphere. Why clouds look white is an interesting question, and I will come back to it later in my talk. But I would like to take this chance to get back to our basics of trying to understand the origin of color. Like most of the colors that we see in nature comes due to the fact that molecules which are called as pigments or dyes which absorb or emit light. And most of the time we see the absorbed light, and in night sometimes we see an emitted light. For example, when we see an radium light in the highways, or when we burn a cracker and it gives a very fluorescent colors due to some ions that emit light. So the absorption and emission are the fundamental things that gives color. But these are not the only things in nature that gives color, like the sky looks blue just because of scattering by the molecules. But similarly, there are other ways one can make color in nature. And one important thing, the way we see color in soap bubbles, because the molecules which makes the soap is not colorful. They are not dye molecules. They are fully transparent. But if you make a bubble out of this soap, they give a very bright luminescent colors because they scatter light from 2 different interference on the soap film, and this interference of this light gives rise to a color. Similar thing that happens even with the feathers in peacock, and this very small structural grating on the feathers of the peacock give rise to this interference from the multilayer, giving rise to very vibrant green-blue colors. You might also have noticed the soap film's color changes dramatically over time. That is just because the soap film thickness changes, and the change in thickness results back into change in color. There is also another way that we have observed color in like CD or DVD, the old technology probably many of us have forgot. They give this color because of the diffraction patterns, and this diffraction patterns comes because of the grating on the CDs which scatter light at different height, and they interfere due to small phase difference in the light that give rise to this color. And exactly similar phenomena happens on butterfly wings, just because the way how the wings morphology or the surface structuring give rise to this color. One thing we all need to appreciate is, unlike dyes or pigments which bleach over the period of time, like for example our clothes lose their color from the day when we buy to the day when we wash them and wear. They lose their color is just because they bleach. Whereas the structural colors are very bright and they don't lose their color all throughout their life as long as there is structure which is not damaged. So the color just originates just because of the fact that things are very periodically arranged in a very regular manner. But there's also a very interesting fact that with completely disordered medium and completely randomly arranged, one can still get a color. And this color that we see in clouds or waterfalls, that's predominantly white. Like if you go to the top of an mountain like Budangiri or some other mountains, you see these large clouds and they are all full white foamy in color. And that happens just because there's a large cluster of water molecules that scatter light everywhere of all wavelengths. That give rise to this white color. And same thing happens with the waterfalls when the thickness of these falls are very big. However, in nature there are very unique birds and beetles or insects that make color out of this completely random medium. And these origin of color in these kind of random scattering is at the heart of many research topics, and we are still trying to understand how to mimic them and make artificial devices or color displays out of it. So today I'm not going to talk about these things. These are all at large micron scale. We can see them, we can perceive them with the eyes, or even just looking at them in microscope, we can really understand the structure and color correlation. What I'm going to talk today is about how to make these colors at extremely small length scales. The length scales which are 1,000 times smaller than the microbe or a bacteria that we were talking yesterday in the two different talks. So these extremely small length scales, things completely become invisible. And what is the point of getting color at that level is the question, and what are the implications of it, and how can we utilize that color for doing some day-to-day optics or even day-to-day technology. I hope by the end of this talk, what I will leave with is a curiosity. I hope you will end up with a curiosity about where does this light originate from, or where does this color originate from, and how to utilize this color at extremely small length scale, and what are the research implications of such color. So let's get back to this color at extremely small length scale. So here what I have put in is just a block of gold, just big chunk of gold, which looks obviously like a metal with bright yellow color, fully reflective. But now I chop this metal into a very small, tiny pieces. So tiny that they are much smaller than a bacteria, or even like million times smaller than the thickness of our hair. What do you think would be the color of this gold would look like? Do you think it will become transparent, or do you think it will still look like a bright yellow color? The answer is it looks red, and it is really surprising. And this was a puzzle at some point, but we now understand why it looks red. And in fact, Michael Faraday was one of the early person who made these gold nanoparticles, like very tiny pieces of gold. So we call them gold nanoparticles. And these gold nanoparticles look red. And the samples of these gold nanoparticles that he prepared 170 years back are kept in a museum, Faraday Museum in London, and they still look red. So they are highly stable, and they look completely different from what bulk gold would look. What is even more interesting, and even Michael Faraday probably might have not thought about, is we can make this gold into different small architectures. Like we can make these gold nanoparticles like a rod shape, which looks blue in color, or a triangular shape, which looks red in color, or make this triangle little bit deformated, making it yellow in color, or make it like a circular, then it looks green. And these just geometrical changes in the shape of the particles give rise to completely different color. So the structure color correlation has a very large freedom in terms of utilizing this color for various technological implications and various practical purposes. But the question is, what is really causing this origin of this color? Where is it actually coming from? It actually comes from the fact that these metals have free electrons, and most of us know that there are conduction electrons in metals, and these metals interact with light in a completely different way. When we shine light on these metal nanoparticles, these electrons in the metal undergo collective oscillations, and these collective oscillations give rise to a light of certain color. In fact, there is a way that we can trap this light. This light need not go everywhere. We can trap it into a very small length scale just by putting this metal nanoparticle on top of a flat mirror. Just take a flat mirror and then put this colored nanoparticle above it. What happens is the light that is scattered by this nanoparticle reflects back from the mirror, and that reflected light scatters back from the nanoparticle. So this multiple scattering back and forth between a mirror and a nanoparticle give rise to highly confined light in a very small length scale. And here the gaps are like as small as 1 nanometer, like it's as small as a molecule. And the specific point about these trapped light is they have a very specific color. They are highly confined. They are extremely bright. So they are extremely sensitive to any geometrical changes in this area. Like any small modification in the shape or the diffusion and movement of single atoms and vibrations would completely change the color and becomes an extremely sensitive medium. And this trapping of light is not new, obviously, that people have thought about this, or even ourselves, we have seen it in daily life. If you go to a barber shop or in a saloon, a beauty saloon, you see that a mirror which is in front of you and a mirror which is on the back of you. You will see yourself multiple times in a mirror just because the light bounces back and forth multiple times, giving rise to multiple reflections. And sometimes this was even also used in like jewelry shops just to give an extra flavor to the whole architecture. So this trapping of light, now we have made it possible to do it extremely small length scale. We call it as a nano hall of mirror. And the great advantage of this nano hall of mirror is, imagine we put in one single molecule in this tiny gap, which in which the light is extremely confined. It's like trapped in that small area, and you put a small molecule, and all these molecules have their vibration. So the molecule starts vibrating. At the same time, it interacts with light. So this interaction between light and molecule gives rise to a new kind of scattering. In fact, the scattering between light and molecule was well studied almost like 70, 80 years back by Professor C.V. Raman. And his whole study of understanding how molecules interact with light gave rise to a Nobel Prize in 1930. He called it as a molecular diffraction of light. What basically he did is like he shined light to a gazillion number of molecules, like a Avogadro number of molecules. And what you end up seeing is these molecules, as they vibrate, they emit different colors. And every bond vibration has a very specific color associated to it. Like C double bond C has a very specific color. C sulfur bond vibration has a different color. C hydrogen bond vibrations are completely different color. So at that time he called it as a new radiation, but now everywhere across the globe are calling it as a Raman scattering. And Raman scattering spectroscopy is utilized across the globe for characterizing molecules, and the spectrum that you get for a molecule in its vibrational spectrum is called as a fingerprint Raman vibration of a molecule. And this fingerprint has been utilized for characterizing the molecules in airport securities, even you put it in the currency notes to see, or even in the paintings, like to see what kind of pigments are there. So it's like a fingerprint. Unique nature of the molecules can be revealed just by looking at the vibrational spectrum of the molecule, which is basically light emitted by the vibrations of the molecule. In fact, Raman might not have thought that this one day the spectroscopy can be done at one molecule level. So now we're using this highly trapped light in extremely small length scale. We can put one small molecule and watch the vibration spectrum of this molecule over the period of time. This opens up a whole new area of how to understand the physics of molecules as it vibrates at room temperature, and how to utilize molecules for chemistry purpose where the catalysis happens. I have been looking at this vibration spectrum or the trapping of molecules for some time now, and what we found is in this highly confined light where you have a nanoparticle and a flat mirror, one can put a molecules that emit light. If molecule emits a light, whereas this structure also scatters that light back. So, and then molecule absorbs and then emits back. So this cycle happens multiple times. Molecule emits, scatters, the trapped light scatters, and then the molecule emits back. This exchange of energy between a nanoparticle and a molecule give rise to a new energy states. And these hybridized energy states between an energy in the molecule and the light gives rise to a new light matter coupling, which have completely different chemistry, completely different energy states, electronic states. And this has opened up a whole new area of how to control quantum chemistry using light, which was always being hard and never been accessible before. As well as for physics purpose, it has opened a new direction of how to utilize molecular vibrations for doing physics, because each vibration in the molecules are considered as a springs, and as a spring vibrates, how does the color of the light change? In fact, in the last few years, we improved upon this technique to not just to position one molecule at a location, but can put a molecule at a very specific location using DNA. And we all know DNA has a unique basic units like ATGC, which are like nucleotides of the DNA, and each point in the DNA is individually addressable. And there is a whole new area of making materials using DNA. You can take a long thread of DNA, which is like a linear thread of DNA, and then knit it, like the way how we knit our clothes or a sweater or something. We can knit it using chemical methods to an arbitrary shape of our design. So in this particular case, I have knitted a DNA origami plate, which is square inch, and every point in this DNA origami, it's very small, it's like 40 nanometers wide, but every point in this DNA origami now can be individually addressable. So you can position a molecule at any given point with deterministic location. So we have been able to put those molecules into this DNA origami and understand how this light matter coupling works and how the molecules emit light. And in fact, the light emission from the molecule becomes 1,000 times brighter, which initially thought was impossible to achieve. Now, it's basically what it says is like, I can take any molecule which emits light and make it 1,000 times brighter, or make it to live or stay longer for more sensitive experiments. For chemistry viewpoint, you can actually do like as I said, you can do a Raman spectroscopy. You can look at the vibration of the molecule. And in this particular case, what is done is you take a molecule which has a very unique bond vibration. We see triple bond C. And most of the chemistry people would understand that C triple bond C has a strength of vibration much larger than C double bond C or even C single bond C. So C triple bond C, which is an sp hybridized bond, has a very high energy, and we can watch the vibration of this one single bond sitting in this trapped light can now give the unique fingerprint vibrational spectrum. And like all textbooks say, you have one bond, you have one vibrational energy, and that vibrational energy won't change. But in fact, in experiment, what you see is the vibrational energy is changing over the period of time. And it's very hard to understand why does a bond vibration would change. It's carbon is carbon, it's sp bond hybridized, so there should not be no change in the vibrational. But it turns out any small local change as the molecule bends, flex, and twists, this bond energy slightly changes. And this slight change in the bond energies are at the heart of how catalysis work, or even at the heart of how protein binding or how functional groups understands their orientation and attack each other at a specific location. So in this particular, what is happening is a gold nanoparticle which is coming very close to this bond. As this molecule moves around and twists, this bond energy keeps fluctuating over the time, and which we were able to observe this now in real time. In fact, what people have done is taken this method one step ahead. They have, instead of using a nanoparticle, you just take a very sharp metal tip and then put that sharp metal tip very close to the molecule. So what does this sharp metal tip does? It's like a lightning rod effect. Like if you have a lightning, all this energy goes into the tip. So if you shine light onto this metal tip, all this energy goes into the tip end, and that's where the molecule is positioned. So one can take the Raman spectrum of the molecule at a specific location in the molecule, and as the tip is scanned over the molecule, you end up having different vibrational spectrum. And this different vibrational spectrum corresponds to different bond vibrations, which are spatially separated in a molecule. And this is probably the first or the very first experiment in which people have been able to see the vibration of the molecules and map the vibration and where the energy is dislocated in the molecule. And these kind of experiments are not just revealing how the whole field of chemistry and the metal interaction work, but also giving new insight on how to design new catalysts for various different reactions. So this is all fair and good, but what can we really do with this is something that I have been wondering for the last 2 or 3 years. And one critical problem in the current world is of understanding how cell membrane works. And this is a picture that I took from an undergraduate biology textbook. And every biology textbook would tell you that cell membrane is a bilayer system. You have lipid molecules which diffuse in time, and at the same time, this bilayer accommodates lots of different proteins, different enzymes, and also has cholesterol, which makes it very complicated system to understand, especially because it also dynamically changes at room temperature. So how can we understand this was my question, and we tried to assemble a very artificial cell membrane onto a mirror and then put a nanoparticle on top of it to create a trapped light onto a lipid membrane and watch as the molecules move around. Can we see the molecule coming and going in this trapped light? So what I show in the next slide is a video of these nanoparticles, individual nanoparticles taken in a microscope, and we will see how they move in real time. Yeah. So I hope many of you can see this video. There are these individual bright spots which corresponds to individual nanoparticles. When I play this video, you will see that these spots or these individual nanoparticles are moving around. And that's from the fact that these lipid molecules are moving, and that moves the nanoparticle also. You can ask, does the color of this nanoparticle change as it moves around? The answer to these two questions are very important, almost like a red in color. So the scattering wavelength, which is 630 nanometer, which is red. But as they move in time, they change their color a tiny bit. And this tiny bit change in color is telling how the molecules are flexing and bending as they move around, as well as how the molecules are diffusing not just in the plane X and Y, but also out of plane. So the molecules go and reorganize themselves in all 3 dimensions. Even though the classical lipid membrane has always been taught as if it's a 2-dimensional membrane, it can move only in 2D, but the things can be very complicated at very small length scales. So this is well and good, but what is that people have been trying to do with this trap light, because these metal nanoparticles have been around for more than now 20 years or so. Are there any real practical applications that they have came out? And there are amazingly large number of applications that have came out. I have picked only 4, which I thought probably are very interesting and are at the heart of my research. So One such application is of making these nanoparticles in a roll, it's like a wallpaper at a kilometer scale. One can do in building coatings or in car coatings, where the color of a car or a building can be changed on demand. And this all color is non-degradable. So unlike paints which degrade over the period of time, these colors should be stable and stay for like forever, and the color can be changed whenever you want, which is nice. But this exactly same phenomena can be utilized as the trapped light is very sensitive to the small change in the molecule movement or the binding and unbinding events, have been utilized to study how the antigen-antibody interaction works. And I hope at least now all of us have came across these antigen-antibody interactions and their importance in designing drugs or finding new ways to cure different kind of diseases. So that has taken up into a very good direction. What I have not talked about today is a technological viewpoint. So like 30 years back, people would have easily seen this kind of antennas on top of everyone's home. Like everyone would have had a TV antenna on top of their home. But now it's almost like, okay, it's gone like by 80-90% of the homes don't have any TV antennas anymore. That is because of the improvement in the technology where now everything happens through satellite. We don't need antennas at that large scale. Everything is miniaturized in our mobile phones or remotes. So probably next 20-30 years, we will see a further miniaturization in these technology. So we will start using these very small length scale antennas made using the nanoparticles, and this will further decrease our size of our mobile phones probably by 100 times and makes it like 1,000 times faster. It has a whole new area which I will not talk to most extent today at all. But there is also a very interesting area where these nanoparticles are giving great attention is in terms of treatment for cancer. As I told, these nanoparticles trap light, but in the process of trapping light, they also trap heat. So you end up creating a very localized heat. So these nanoparticles are delivered to a very specific location at the tumor points to kill cancerous cells locally without killing any other healthy cells. So this localized heat to kill tumor cells has resulted into clinical trials, and people are hoping that this will emerge out as a potential treatment for cancer. We don't know yet, but it's a very potential direction. But my vision for utilizing these systems goes way beyond just diagnostics. I'll just give two examples from nature and how nature utilizes color. Yeah. So one example is chameleon. I'm pretty sure most of us have heard chameleon all throughout our childhood and even now. And the good thing about chameleon is it can camouflage. It can change the skin of its color on demand when needed. So I'll just play this video. I hope people can see this chameleon is changing its color from green to blue now. As the light shades on it changes, which is in this video on the top right, top left corner, it now gradually now changing it to slightly whitish blue. As time progresses, you'll see that it's it now changed it to like fully brown. It's like slightly orange color depending upon given specific conditions. Chameleon is great, but extremely good at it. That is, this animal is at deep of the ocean. So in this central video, what you are seeing is the video that is taken at the bottom of the sea. And what you see here is a plant and there is nothing much happening. Now I'll play the video, and I'd like audience to try to see whether they can point out any big animal. Yeah. So let's see. So now we can see there is literally nothing much is happening. There is just this small little plant. Probably a fish comes now and then goes out, but nothing has changed. But suddenly there is something happening. Yo, you can see like out of that plant, some other new match to the new background. This is just amazing, the speed at which it does, and the texture, the rapid dynamic adaptive is amazing. I'll try to play this video again in a backward way. Let's see. Yeah, now I'm trying to go in the backward direction to see how it was actually hiding in this plant. It doesn't make any sense. Yeah, this was all this chaos when it was getting off that plant. Yeah, you see this? So this whole big animal, marine animal, these are called as cephalopods. This cephalopod was just sitting on this tree, like all the time. It was just sitting. It was extremely hard for any one of us to spot it because it was camouflaging this color to the color of the tree, as well as the texture was exactly the same as the texture of the tree, and it was almost impossible for anyone to find that there is an animal which is hiding there. And it suddenly, within the fractions of seconds, it suddenly emerges out of it with bright, big eye and increases massively in its size. Yeah, and then runs so fast away from one spot and then goes to a next spot and hides into a new place. This is incredible, and there is nothing, to the best of my knowledge, we have been able to artificially make any material that can change color at that fast rate or at that level of complexity. So the vision for utilizing this color goes all the way to utilize it for doing diagnostic at cellular level. So all the current day diagnostics, we need to have a surgeon who is cutting through our skin and doing the surgery. But at some point, I would like to see utilizing these nanoscale machines which can explore the areas in the body and identify the parts which are not being functional properly and repair on demand and monitor them regularly. So this on-scale nanomachinery for biological systems is a new direction where people are thinking that it has a potential for new medicine and new point-of-care diagnostics thing that one would want to have in 40, 50 years from now. So I think this is the kind of new area where people are putting a lot of effort in. I'll just quickly show what is the level at which we are now. This is an amazing work, but the level at which we are now is like, you can see just a nanoparticle which is coming. It's like a long nanorod. Like, I'll play it again. So this long nanorod comes and sits onto this cell. This is a live living cell. And then it tries to poke through the membrane, but it cannot. But it just goes and sits there. This is the level at which we have got to. We can make these nanoparticles, drive them to a very specific location, and the next bigger challenges is to how to obtain molecular signatures from it, how to control the direct, how to utilize them to do assemble and disassemble and do surgery on demand, how to monitor their progress, how to get them out of the body is also another big question. So, and obviously this kind of research doesn't just require expertise either in biology or physics or even mathematics. It needs a skills and team of researchers working across the discipline. I hope with this last 30-40 minutes, I gave you a broad overview of what nanoscale is about and what is the color of nanoscale looks like and why we are more interested in about. And one key take-home message I want you people to take is the light at nanoscale is extremely bright, and this bright light is being used for sensing to see things at nanoscale. So it's our eye at nanoscale. Otherwise, we won't be able to see anything. And this is being utilized for not just biodiagnostics or making new materials or control the properties of the molecules, but they are also used in technology and biomedicine. So there is a large whole new avenue of research and new technology will be emerging probably in 10, 15 years. And I hope we keep our eyes open and keep exploring this field and be more curious about what nanoscale color looks like. With this, thank you very much for your attention, and thank you very much for the organizers for putting together this webinar going in extremely good shape. Thank you very much.
Hello. 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 ಸರ್ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಾ ಇಲ್ಲ. ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗ್ತಾ ಇಲ್ಲ. ಅಲ್ಲ ಅಲ್ಲಿ present now. Your entire screen. I would like to thank ಹೇಳ್ಬಿಟ್ಲ ಹಂಗೆ ಅಲೋ ಮಾಡೋದು ಅದನ್ನ ಔಟ್ ಆಫ್ ಥ್ಯಾಂಕ್ಸ್ ನಮ್ದು ಅದೇ ಸ್ಕ್ರೀನ್ ಶಿಫ್ಟ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡೋಣ ಅಲ್ಲಿ ಬರ್ತೈತಿಲ್ಲ ನೋಡ್ರಿ ನೀವು ಅಷ್ಟೇ. ಬರಕತ್ತಿದ್ದಲ್ಲ ಅಲ್ಲಿ ಮಾಡಿದೆ. ಇಲ್ಲ ಬರ್ತಾ ಇಲ್ಲ. ಬಂತು ಒಂದು ನಿಮಿಷ ಸರ್. Sorry for the disturbance, participants. I would like to propose the vote of thanks. With the blessings of Shri Gavisiddeshwara Mahaswamiji, we have successfully completed the 2 days international webinar on recent trends in microbes and chemical sciences. For this, first of all, I would like to thank the distinguished speakers, Dr. Mahadesh V. Patil, Professor and Head, Plant Pathology Division, University of Agricultural Sciences, Raichur, Extension Leader, AWC, Koppal, for his speech yesterday. And I also would like to heartily thank Dr. Syed Dastagir, Principal Scientist, National Collection of Industrial Microorganisms, CSR NCL, Pune, Maharashtra, for giving a lecture on multifaceted microorganisms and their use in biotechnological applications. Today we have done 2 sessions. In the first session on organometallic catalysis, Dr. Srinivas Budhgumpi, Group Leader and Associate Professor, Center for Nanoscience, Nano and Material Science, University of Bangalore, has given a beautiful lecture. Thank you, sir. And in the session 4, the Dr. Rohit Chikreddy, Title A Research Fellow, Trinity College, University of Cambridge, UK, has given a lecture on how does nanoscale light look. I thank all these distinguished speakers for their support and giving the lecture. I hope all the participants have got benefited from this. And next, I would like to express profound gratitude to our secretary, Dr. R. Maregoda, for his support. And secondly, I would like to express my vote of thanks to the retired principal, Professor Manohar Dadmi, and NAC Special Officer for his constant encouragement. Next, our chairperson of the webinar, Dr. J.S. Patil, for his support in all the respects. He has supported in arranging the sessions very nicely, and the teaching staff of our department, always they have extended their warm extended their handing help for conducting the webinar. I thank all the teaching staff of our college, one and all, and the non-teaching staff, they have also given the support for the organizing the webinar. I thank all the administrative, that is office staff, for their support. And without the participants, this would not be a grand success, definitely. And the participants are have played main role for the success of this event. I thank all the participants. Hope that they have got benefit from this webinar. Once again, I thank all the participants, all the speakers, the management of SGVT Trust, teaching staff, non-teaching staff, each and everyone. Thank you one and all, making the event grand success. Thank you.